Well, thank you very much for having me give this talk here. The main purpose of this talk is to highlight some of, in line with the topic of the workshop, to highlight some of the theoretical structures that have appeared in classical scattering amplitudes in gravitational theories over the last number of years. And in the process, of course, also describe some of the state-of-the-art results, and also hopefully pique your interest with some single scale and multi-scale integrals, and also that we could certainly use your help with, or at least some of your help with. And also pique your interest with some open questions, which don't necessarily relate to integrals, but relate to structures that we don't exactly understand, or that at the very least we don't know how to use. This talk is based on work with many people, some of whom are in this room. So it's V, Donato Bini, Thibaut Damour, Stefano De Angelis, Assad El-Khidir, Andrea Giralico, Aidan Herdershi, Enrico Herman. We can spend the rest of the talk reading names. Donald O'Connell, Julio Parra Martinez, Mikhail Ruf. There's a typo there. Chao Shen, Volodyan, Sasha Smirnov, Mikhail Solon, Fei Tang, and Mao Zeng. I think I didn't miss anybody. Right, so the first question that is usually asked when you see scattering amplitudes and gravitational theories in the same sentence is why? Why would you mix the two? Of course, we have our own favorite answers, but rather I will appeal to a higher authority to answer this question for me. The first two answers that are given are the usual ones that we give, because we can, and because they're there, and because something could go wrong, and if it does, then something is interesting. But with a lot of foresight, Weinberg predicted that it's interesting to look into infrared properties of gravitational theories, in particular the properties of soft gravitons, and he was really fascinated by that. That there is some analogy with electrodynamics, and soft gravitational radiation could in fact be very useful and very interesting. And indeed, 50 years after the fact, we have actually seen that soft gravitational radiation. It looks like this. These are the soft gravitons. So now we can say with a straight face, gravitons exist, and we can do quantum gravity with Feynman diagrams, because those are in fact the building blocks. All right, now as detectors get better and better. Oh, I should say what you see here is actually the space-time metric at infinity, or rather at the location of the detector. It's of course infinity relative to the place where the event took place. But again, this is the space-time metric, and this is, in this case, the metric is an observable. And what you see here is basically this. One direction goes longer, the other one goes shorter in a correlated fashion. Now, of course, as detectors get better and better, precision, their precision grows better and better. So in the not too distant future, we'll have a couple of orders of magnitude increase in the frequency. Current LIGO is the gray band here. This is in some distant future, but it's there. So we'll have a couple of orders of magnitude in frequency, in sensitivity, at the current frequencies, and at much lower frequencies we'll have signals that last basically forever, for years, months, certainly days. Current signals, as you see here, they last for a couple of seconds if we're lucky. So because of this, it's necessary to have theoretical modeling for long signals, and in these theoretical models, we need to avoid the buildup of theoretical errors, which appear because our analytic calculations have some, they truncated some order, and there are errors of that order. Also, it will likely be important that all the various approaches to two-body problems will need to work together to lead to sufficiently precise theoretical input. Now, here are the things that we can do at the moment. with two-body problems. So of course, a numerical relativity, in a perfect world, we would use it because it gives us the truth. In our world, which isn't perfect, it still gives us the truth. It's expensive. It's not terribly precise at the moment. And of course, it doesn't cover the entire parameter space. So because of this, we need to supplement it as much as we can with analytic calculations. And here are the three approaches, the three current approaches to either in spiral or scattering. There's the post-Newtonian expansion, in which one expands in velocity and also in GM over R. This is a great expansion for quasi-circular orbits because by virial theorem, these two are of the same order, and they're also relatively small, so one can expand in them. And this covers the purple plot up here. There is the post-Minkowskian expansion, in which one expands in GM over R, but keeps exact dependence on velocity, which is, for that matter, which can be assumed to be of order 1. Well, this is what in field theory we call perturbation theory, basically. And it covers the orange triangle here. So there is a region for it. There is a region in which post-Minkowskian expansion is important for bound orbits, anything below eccentricity 1 and orange right here. And of course, scattering is post-Minkowskian. There is no virial theorem for unbound orbits, so there is no correlation between velocity and GM. And last but not least, there is the small ratio expansion, also known as the gravitational cell force, in which both GM over R and V square are of order 1. There is no expansion in them. There's an expansion in the small mass ratio. So one starts with a probe moving in a Schwarzschild spacetime, and then one takes into account the self-interaction of that tiny particle with itself, and that produces corrections of the order of the mass of the probe divided by the mass of the Schwarzschild spacetime at various parts. Okay, so I left behind unfinished the idea of precision. This is what we know at the moment. In a post-Newtonian world, we know the dark, whatever this color is, and also the red rectangle in a post-Minkowskian world. And people who do gravitational wave observations and modeling tell us that to meet the precision needs for foreseeable detectors, we might need post-Newtonian calculations that cover the light, whatever this color is. So a few more orders in G and in velocity, or in a post-Minkowskian world, we need to basically fill up all this. We need to extend the red rectangle to cover the uncovered line. So up to G to the 7 and perhaps up to V to the 12. Of course, this is for non-spinning probes and assuming for non-spinning bodies and non-deformable ones. One should, at some order, actually at the current order, one needs to account for spin and also for dissipation and also for tides and so on and eccentricity. So there is this is really a cartoon of what's needed. All right. So our approach, because we are field theorists, our approach is scattering amplitudes, or more generally field theory. We are not using Einstein's equations. I should say this: our work doesn't really come in the vacuum. Einstein's equations and intrinsically general relativity methods have been used for the two-body problem since, well, I don't want to say the beginning of time because, but 30 years, 40 years or so, this is in fact great for us because we come with new methods, so we get to compare. We have, we have anchors in the results that have been obtained by other means. The main character in our work is the graviton, the spin 2 particle, which looks like this at the moment. And these methods are well suited for a collection of questions that have to do with asymptotically flat spacetimes, perturbation theory, and relativistic gravitational wave physics with compact sources. So it provides a complementary approach and complementary results to stuff obtained from geometry and Einstein's equations. It also, because it deals with asymptotically flat spacetimes, it avoids subtle aspects of coordinate choices. Therefore, it makes a comparison easy between various approaches. And also, what do I mean by that? I will get to the subtle aspects in towards the end of the talk. Excuse me. So there are some subtle aspects, and there are that I will get to at the end of the talk. And there are some other subtle aspects that, for example, if you take two numerical simulations and done by totally independent people, each of them has some coordinate choice in space-time. But the question is, how do they align the asymptotics of those coordinates if they haven't aligned them in the beginning? Here, everything is flat, Cartesian coordinates. So even a numerical relativist, if they want to study scattering, they will still pick flat coordinates because there is nothing at infinity. So it's this kind of subtle aspects that are avoided here. And there are other subtle aspects that have to do with, you know, symmetries of flat spacetime at infinity. And those are not avoided, and they are important. And I might get to them if I speak fast, but I'd be happy to tell you about if I don't get more questions. I should say, of course, this is, even though it's a slide stock, the intention was to spare you the beauty of my handwriting. So please feel free to interrupt and ask questions anytime. Just as if, imagine that this were a blackboard, so just written a little faster. Right. So where are we? Okay, so why field theory and why point particles? Field theory is, of course, the theory of point particles to the extent that, at least in the beginning. So, of course, at large distances, any finite-sized body appear point-like. And if one cares about finite size, of course, one could attempt to include finite size effects via multiple, as a multiple expansion in an effective field theory type framework. Why relativistic or post-Minkowskian? I guess I addressed that. There are velocities don't need to be small. They certainly aren't small in a scattering event. They don't need to be small even in an eccentric bound system. So relativistic corrections could potentially be important, and they are. Why quantum versus classical? That is a great question. It turns out that quantum calculations are substantially more constrained than classical calculations. We get to use concepts like unitarity that we might not dream about in classical physics. And these actually simplify our lives, at least. And as it turns out, this approach reveals some of the structures that I'll be talking about. Why scattering? Well, as I was addressing Matthias's question, scattering is clean from a numerical perspective. Again, asymptotic space is still flat, and just like in an analytic approach. And because of this, the alignment of coordinates is straightforward, and therefore there is a relatively easy exchange of information between analytics and numerics. Now, scattering itself might be detectable in some future, and in fact, there is already a candidate event for, if you wish, a half scattering process. Basically, this part. Come on. Basically, this part, either the first part or this part here. It is a candidate event for dynamical capture. So basically, a two-body system which has negative energy, but it's almost zero. So it came in, there was radiation, and then the incoming body was captured. And then there are also other subtle aspects that that need to be addressed here. Nevertheless, a question that needs to be answered, which I will not answer, is how to connect scattering to the to bound orbits, and because ultimately that's the vast majority of current signals. But at least for the purpose, this is a very important question, but at least for the purpose of today's talk, this is a secondary question. So again, this is field theory. So we get to use our entire set of toys, and they all have a place in here, including the ones that are in the dots, because I don't know what they are. But if you tell me one, I'm sure we can find a use for it. But most importantly, the classical limit is something that helps and makes all of these methods substantially more powerful than they are in regular quantum regime. And we'll see exactly. Right, so having said this, there are many field theory-based approaches to observables in the gravitational two-body problem. And here is London Underground for you in field theory methods. Everybody starts with their favorite formulation of gravity plus matter, regular four-dimensional field theory, some effective field theory that accounts for the small mass ratio, for a small mass ratio, some worldline methods, Post-Minkowski and EFT, or worldline quantum field theory. And after following various paths in this on this chart, one finds observables, either complete observables or conservative observables. Now, everybody at some level or another has to pass this bridge that takes us from an integrand, which ultimately look more or less the same. There are certainly the same type of integrals in pretty much all methods. One needs to pass the bridge of integration, and this is where the current bottleneck is. And here, many of you know a lot more about this than I do, so maybe you can educate me about this afterwards. Right, so the plan. The plan is to talk a little bit about classical physics and how to get it from quantum physics. I will also talk about the consequences of this limit for integrands, integrals, and observables, and also discuss a little bit some state-of-the-art results. And in the process, I will indicate what I promised, namely some structures that appear both at fixed order in perturbation theory and also at all orders in perturbation theory. And also, hopefully, I hope to catch your interest with some of the open questions. All right, so classical physics out of quantum physics. Let's see. Anybody remembers from their quantum field theory course that classical physics is tree-level? It's given by tree-level amplitudes. Anybody remember? Anybody else remembers this? So 2 yeses. All right. That is certainly true, but it's not always true. That's absolutely correct. It is not true if it's true if the only H bar is the H bar that we see. It's not true if there are H bars that we usually don't see. In our case, there are some H bars that we don't see. They are buried in the mass. So if we expose them and then we take the H bar to zero limits, then we get something else. We don't get tree-level amplitudes. We actually get loop amplitudes. Now, intuitively, one might guess that loop amplitudes have to play a role in this game, because even if you look just at the orbit in pretty much any observable in general relativity is a non-trivial function of Newton's constant. Tree-level has a very specific dependence on Newton's constant. So where does all that come from? Well, it can only come from loops. Another way of understanding this is to set all H bars to 1. And if you ever talked to Misha Schiffman or people in his crowd, you will learn very, very quickly that if you don't set H bar to 1, you cannot proceed past this slide. So another way is to set H bar to 1 and use the correspondence principle that says take all the charges that appear, take them to be large. And according to Bohr, this should give us the classical limit. And indeed, in this case, there are a couple of such charges. External momenta, for example, are such charges. Others are spins and angular momenta. And another way to phrase this, or at least one way to phrase this, is to state that the de Broglie wavelength for rotation or for translation is much larger, is much smaller than the separation between these particles. So if the angular momentum, if the orbital angular momentum is large, B here is the impact parameter, P is the typical momentum. So if L is large, then the de Broglie wavelength is much smaller. So in this sense, the correspondence principle in this language gives us something that is obviously true. We want to stay sufficiently far apart so that we don't feel the quantum nature of each of the parts. So based on this, and also based on the fact that Newton's potential is a classical quantity, it's relatively easy to figure out that the Fourier transform of the potential, the interaction of some effective interaction potential between two bodies, has to look this way. Now, this might look a little strange relative to the words I said, but think of it this way. If Newton's potential is classical, so G over N is classical, G over R is classical, then so is its nth power. If you Fourier transform this, you're going to find this. That's all I said. And the reason I wrote this in terms of momenta is because from a scattering amplitude point of view, momenta are the natural quantities. So basically what we are supposed to do is, one, don't ignore loops because there are G's all over the place here. Don't ignore loops, but ignore most of the loops and fish out only the pieces in a loop amplitude, in a 4-point loop amplitude that contain this particular dependence on the momentum transfer. There is a little bit of a sleight of hand that I'm doing here. There are some logarithms every now and again because we'll get there. And in fact, the same is true if one goes beyond a 2-to-2 scatter, so beyond the conservative process. The reason being that there is no classical suppression to Bremsstrahlung, right? There is classical electromagnetic radiation from moving charges. There is no suppression for it. In fact, at accelerators, that's one of the limiting factors. And the same is true for gravity. So if one is interested, say, in a two matter particle goes to 2 matter particles plus some number of gravitons, it's exactly the same scaling with the momentum Q transferred between the two matter particles. All right, so now we know what we want to compute. Yes. All right, so now that we know what to compute, let's see a simple example, perhaps the simplest example, which I'm sure many of you encountered in your field theory course. How to get Newton's potential and its relativistic generalization out of scattering amplitudes. So the 2-to-2 matter particle, 2-to-2 amplitude at 3 level, due to a graviton exchange, looks like this, where order Q to the 0 contain terms that don't have this 1 over Q square. And they are there because there are 2 stress tensors that are contracted. There are various momenta in there. Once you write them in terms of the dot product of the incoming 2 momenta, there is some other stuff that appears here which cancels the denominator. Now, we don't really care about these because if you cancel the denominator, then it means there is no propagator. It means that the particles sit on top of each other. So that manifestly breaks the assumption that we had that the particles are always separate. In fact, these terms, they're not, I'm sure you encountered these terms elsewhere. And of course, not in a gravitational context, but in a QED context. If you remember your non-relativistic quantum mechanics analysis of the hydrogen atom, or rather of the fine structure of the fine structure of the hydrogen atom, I'm sure you've encountered the Darwin terms. Right? The Darwin terms are things that exist only if the electron and the nucleus are at the same point. Means that they are delta function of R, means that in the Feynman diagram language, they have no 1 over Q squared. So the Fourier transform, which relates scattering amplitude to the potential at that order, is in fact 1. It's independent of the distance. So these are the gravitational analog of the QED Darwin terms. All right, so non-relativistic quantum mechanics tells us how to connect a three-level amplitudes to a potential. There's a Fourier transform. There's also a normalization that needs to be taken care of. We usually, in relativistic quantum field theory, we commute creation and annihilation operators to twice energy times delta function. In non-relativistic quantum mechanics, we commute creation and annihilation operators to 1, or rather just the delta function. So we need to absorb that twice the energy to make the connection correct. And once everything is said and done, this is what you get. The first equal sign is the complete answer, all relativistic of sorts. Written in relatively strange variables, I might add, but never mind that. This coefficient here is just m1, m2 divided by e1, e2. And then if you expand in velocity, you get the first term -1. So gravity is still attractive, even from a Feynman diagram language. So this is Newton's potential. And then there's, of course, a first correction and the second order correction and so on. The first order v square bit here is part of the Einstein-Infeld-Hoffmann first post-Newtonian order potential. Written here from, if you expand this, is written here in isotropic coordinates. And the reason I'm emphasizing this is that you can't find it. I couldn't find it in the literature in isotropic coordinates. Anyway, this is so this is the blueprint of what's going on here. How to connect S matrix elements, or it is a blueprint for how to connect S matrix elements to interaction potentials. At higher orders, things are a little bit more involved, but the idea is the same. But this is also not the only one. And of course, once we have a potential or a Hamiltonian, then we can break out classical mechanics textbooks, solve equations of motion and so on and so forth. But as it turns out, this is not the only connection between scattering amplitudes and observables. There is another one, which is in a sense more straightforward. It's in a sense more direct, though not necessarily more straightforward. And also, it's in some sense, it's also non-perturbable. So I was emphasizing a little bit earlier that from a field theory point of view, we get to use things like unitarity. Well, this is the first incarnation of that. So if we have an S matrix in an elastic S matrix, that is, we have two particles coming in, two particles going out, then unitarity implies that that S matrix is a phase. Right? And here the phase is written as an operator. So this is what happens if we expand it. There is, if we expand this matrix element, there is the identity, and then there is the expectation value of one copy of this guy, then two copies of this guy, and so on. These things are usually referred to as iterations for obvious reasons. There are two of them, and then three of them, and so on. And to construct the operator phi out of S matrix elements, one really needs to subtract these guys. Ultimately, the EFT that I was mentioning in the previous slide amounts to subtract it. It's a way of subtracting. Now, because this is an exponential, then in the classical limit, it surely has to look this way. There is an exponential times 1 plus order h bar stuff. And this is again, these are the S matrix elements. And this I ideally should have some interpretation of its own, but it surely is some series in the coupling constant here labeled by n, and I didn't write the powers of g. And then here, what I wrote are what these m's here are in terms of I, which are I1, I2, I3, which are the analogs of these fellas. And then the integrals, which come from these iteration guys. These z's, it's not obvious here, but I'm happy to describe how this comes about. These z's, or these integrals, they are really just the two-particle phase space integrals corresponding to the product here. And that appears from, for example, inserting a two-particle identity operator in between just to compute these matrix elements. All right, so somehow the S matrix, the elastic S matrix elements should look like an exponential in the classical. So of course, the next question is, what is exactly the thing that fits in the exponent? And I'm sure, actually, maybe before I give the answer, anybody might have a guess. Right, so the S matrix is an exponential. What could be the thing in the exponent? We've encountered this in ADS-CFT in the form of the Aldane-Maldacena S matrix. We've encountered this in non-relativistic quantum mechanics under the name of WKB approximation. Right? One is tempted to say that this thing here must be the action evaluated on a classical solution. Right? In ADS-CFT context is the ADS string action evaluated on a worldsheet solution. In WKB approximation, it literally is a solution to the critical points of the Hamiltonian. The same is true here with a few quirks. Right, so when we find solutions to the classical equations of motion, we usually impose, when we derive the equations of motion, we impose that the boundary conditions are fixed coordinates, because we typically treat P as the derived variables and we vary with respect to X. However, this is not what's going on when we compute S matrix elements. When we compute S matrix elements, we like to fix momenta. So how do we connect fixed coordinates to fixed momenta, or maybe not necessarily fixed momenta, but at least fixed charges, fixed conserved charges like angular momentum or perhaps the total energy. So this is another standard course that tells us how to make this connection, and this is where thermodynamics comes about. The connection between fixed coordinates or fixed extensive variables and fixed charges or fixed intensive variables is a Legendre transform. In this case, what variables do we, what conserved charges do we have? We have angular momenta and we have the energy. So this is the Legendre transform. If we subtract this, then because the energy is conserved is the same as the Hamiltonian is time independent. So basically this addition kills H. Here J is conserved. This thing kills the J d theta term in here. So this IR is actually the integral over the trajectory of the radial momentum times the radial coordinate. This also has a name. This is called the radial action. And it's a standard and classic quantity in classical mechanics. Now, what does this tell us? It tells us that if we compute this, then it's as if we take PR, dr, and integrate it over the trajectory. Now, how do we get observables out of this? Well, the variation of the radial action with respect to its variables, which are now J, E, and perhaps other things, happens to be this one. So why is it this way? We have the original here. We had ds was pdx minus edt. I is s plus et minus dx. So di is t or delta tde minus xdp. This is the same stuff that we write when we connect, say, the energy to the free energy. The energy starts as TDS, whereas the free energy contains an SDT. That's exactly what's going on. So if we manage to compute IR out of S matrix elements, which we should be able to, then just taking derivative to respect to the angular momentum or the total energy will give us the scattering angle or the time delay. And this relation holds to all orders in perturbation theory. And in fact, it holds non-perturbative. I haven't actually used anywhere in here that we are using perturbative physics of anything. So this is what we're going to use most of the time. Oops, okay. So we know what we want to compute. We know at some level how we might want to compute it, namely construct this IR or perhaps construct the Hamiltonian. So now how do we compute it? How do we focus in an amplitude calculation on the classical part? Well, we go back to our little discussion of what the classical limit does and try to enforce try to understand what it's telling us. And trying to enforce those constraints as early as we can, because, well, if we don't enforce that as early as we can, then we run into trouble. Trouble being that we basically repeat quantum calculations and we end up tossing out most of what we do. All right, so the constraints, to recap, are the particles are always separated. There is this specific dependence on the momentum transfer. And then, oh yeah, there is one other thing that I forgot to tell you. So there was this dependence on the momentum transfer, but I never actually told you how the loop momenta should be related to the momentum transfer, right? So the momentum transfer was assumed to be small, but I never told you how the loop momenta should relate to the momentum transfer. Now, let's see. Imagine for a second this. So overall, there's a momentum transfer Q. You can think of this picture as two particles hopping along and exchanging gravitons one at a time. So this is Earth and this is Sun. The motion is relatively smooth, right? We don't lose a lot of momentum and then we gain it back from the Sun. Right? Because if that were the case, the trajectory would not be this, but would be more like that. Right? So this indicates that since overall we're losing Q, these guys should be of the same order as Q. Because if they weren't, then it means that we'll be losing a lot and gaining a lot. So this actually puts us in what's known as the soft region of loop amplitude or of loop integrals. So and then in this region there are this is what I wrote here. This is omega L is loop momentum written in time and space coordinates, and I put them all proportional to Q. And then there are two kinds of loop momenta: those that are always off shell. Here, the off-shellness is given by the velocity of the external particles. And the reason this is off-shell is that it clearly doesn't square to zero. And then, so this means that these guys are can never escape to infinity. They can only be exchanged between particles. And then there is radiation stuff that can escape to infinity. And they have different physics. These guys produce potentials or instantaneous interactions. These guys produce long-range, rather time-delayed interaction, and they both have a place in our story. So what are the consequences of these, especially of the first, actually of all three? So first of all, we want this particular dependence on the momentum transfer. Therefore, we shouldn't allow anything in which matter particles cross. First of all, because particles are not always separated, and second, because if you actually evaluate this integral, it's not going to have this Q dependence. The other thing is that every loop inside any diagram that you might possibly draw should have at least one matter line. If that were not the case, then applying this scaling to that diagram will reveal that, in fact, it scales at a higher power of Q than this. So it is quantum mechanical. And this is also somewhat intuitive. If you have a loop of gravitons, it has nothing to do with the external particles. It is pure quantum gravity. And that's not classical. And then there are other constraints that one might care for. For example, one might care to integrate out only the potential gravitons. That means that one shouldn't include, for example, diagrams like this, because this guy, if this interaction here were, if this graviton or a potential graviton, it means that in a time picture, this point and that point were at the same time. Therefore, because this is an almost instantaneous interaction, therefore these interactions here don't have time to occur. So these guys would be zero if all gravitons were potential. And indeed, if one actually evaluates this, one finds that zero. Now, having said all of this, hopefully I didn't lose everybody. It is the unitarity method, which I will not describe because SV will describe it at length on Thursday, maybe. Unitarity methods provides us with ways to actually enforce all of these constraints. And it does so by telling us exactly which unitarity cuts we should use when assembling an integrand and which unitarity cuts we shouldn't. For example, at one loop, this is the only unitarity cut that we might care for. Of course, technically, one might choose to compute it in a different way than this way, but never mind. This is the only thing that we need to consider, because these gravitons, the exposed lines, are all cut or on shell. So this guarantees that the particles are never on top of each other, and also that there is a matter line inside the loop. Similarly, here at G cubed, that is at two loops, the same is guaranteed by the presence by the exposed lines. And also here, if we were to draw one of these guys, then it would be this diagram. So if we care about the potential, then we don't need to include this. If we care to include further radiation contributions, then we should include. And similarly, at G to the fourth, there are a few more. The first 8 know only about potential gravitons. Last 5 also know about radiation gravitons from these bubbles at the top. And similarly at G to the 5, G to the 6, and so on. So unitarity method tells us, tells us how to take these and merge them into an integrand that we can integrate. So by listing only the cuts that satisfy the properties that they contribute in the classical limit, basically gives us everything that we. Okay, so we know what to compute. We sort of know how we might want to go about it. Now, assume for a second that we have an integrand at the end of this procedure. How do we integrate it? Well, it turns out that there is some more structure that is in there that's worth exploring. So to carry out the integrals, of course, now I was talking about scaling with Q in a sort of abstract way. I didn't exactly tell you how to do it. So let's talk about basically how to do that. It turns out that some special choices of variables is quite convenient. These are not new variables. They have been known in the QCD community since a long time, from Sudakov, Beneke, and Smirnov, and from the literature on heavy quark effective theory. And they were popularized in our context by Para Martinez, Ruf, and Zhang. So the idea is not to use the incoming momenta P1 and P2, but shift them by a little bit, that little bit being half of the momentum transfer. And the reason this is extremely useful is that it kills one dot product. Anything that looks like P dot Q, P bar dot Q is 0. This will have important consequences in integrals. Okay, so what happens with the massive propagators in this organization? Well, this is a typical massive propagator. P is an external momentum, L is a loop momentum, and this is the mass. So if we expand the product, there are two kinds of terms like P dot L and terms like L square. Or we could also put in a bar there if you'd like. So as far as the Q scaling is concerned, this guy dominates over the second one. So wherever we see a propagator, 1 over P square, P plus L square minus M square, we get to expand in this L. So basically the denominators of matter propagators will all be linear of the type P dot L. Some P, some L. That L could be a sum of L's, but no matter. So that's what I'm writing here. So this is a typical integral. Some numerators, graviton propagators, which depend only on loop momenta, and then matter propagators, which become linear. Now, what could this integral depend on? Well, this integral could depend on P bar square. This is a constant. It could depend on P1 dot P2, P1 bar dot P2 bar, which I gave it a name. It's called Y. And it could depend on P bar dot Q. There are no other combinations of that. But P bar dot Q is 0. Therefore, the integrals that can appear are all functions of one variable, Y. And also, because of this, all the mass dependence and all the Q dependence can be scaled up. So the first structure is that to any that we observe in this along this route is that to any loop order, the 2 to 2 amplitudes are sums of integrals, each of which is a function of a single variable. This is extremely important. I'm sure most of you have computed quantum loop amplitudes, quantum 4-point amplitudes. They are not functions of one variable. They're not happy. These guys are a lot happier. Okay, now that's not all. There's more that can be said based on the fact that one, all the mass dependence can be made explicit, all the Q dependence can be made explicit, and and that is, we can in fact constrain the mass dependence of a classical amplitude. So this is one other way of writing the classical amplitude. This puts together the Q scaling that I was describing earlier. Oops. And yeah, the Q scaling that I described earlier. And also, I restored a whole bunch of masses here. This M is meant to be the total mass. The way I restored it is I wanted these A's to be dimensionless, so I just stuck in M's to give this thing the right dimension. Okay, now comparing this with whatever we get out of this kind of Gedanken calculation, it transpires that this product, a to the L, m to the L plus 4, is a to the L times m to the, this m to L plus 4, is a polynomial in these masses. Out of these integrals, there is no way to generate inverse powers of masses. There are only positive powers of masses. So this is a polynomial of degree L plus 4 in M1 and M2. Because there is always at least one tree-level graph. But there is either one of these lines couples to at least one graviton. It means that there is at least one factor of M1 square, M2 square. There's an M1, M2 for each of these. And then last but not least, it's important to remember that in any Feynman diagram that's Lorentz invariant, there is no way to generate 1 over M1 plus M2, 1 over the total mass. So with this in mind, let's write the most general polynomial of degree L plus 4 in M1 and M2. And it turns out to be this one. That also has this guy as an overall factor. So here nu is the symmetric mass ratio. So basically here I wrote the most general pluses stand for plus up to coefficients. So this is the most general form for this AL m to the L plus 4. So the consequence of this writing of this organization of integrals that can appear is that the finite part of the classical part of a 4-point amplitude is a polynomial in this symmetric mass ratio, and the degree of that polynomial is the integer part of the loop momentum over 2. Sorry, the integer part of the loop number divided by 2. This is known as a good mass polynomiality. It was originally observed by Wine, Steinhoff, and Bonanno in explicit calculations. It was understood by Damour from GR point of view. Here, it is understood from the structure of Feynman diagrams, scattering amplitudes, and Lorentz invariants. So, yeah. All right. Any questions? This is boring. Can I go faster? Is this too fast? All right. So we are almost there. Well, I don't know where there is actually, but never mind. Right. So the last thing to talk about is these guys. We have everything else. The last thing to talk about is integrals. So the integrals, yeah. No, or at least I'm not aware of one. Basically, the difference is here everything is manifestly parity invariant with, and everything is manifestly symmetric under M1 and M2. The fact that there's an asymmetric mass ratio says that that asymmetry compensates another asymmetry that comes from the spin, and including that is not obvious, at least not right now. But yeah, it's a good question. Right, more questions? Right, integrals. Again, here you guys know more about this than I do, so please feel free to chime in. So the idea is the sort of the standard beaten path. We take the integrals, these I of y, the single scale integrals, with linearized matter propagators. We reduce them via integration by parts reduction to master integrals, and then we construct systems of differential equations for them. At 3 loops, why 3 loops? Because earlier you don't need any of this machinery, at least not necessarily. It can be done basically by hand. So at 3 loops, this is you find such a system of differential equations with mostly rational a's and with variables z that are either x, 1 plus or minus x, and 1 plus x squared. This is the relation between x and y. There's a change to a canonical basis, meaning that there's the epsilon out front. So and again, this B is here, this matrix B is rational. Therefore, it's the solution to this differential equation is mostly to this differential equation in terms of generalized polylogarithms. The order in epsilon to which we need to integrate it depends, of course, on the coefficients of the various master integral of the coefficients of the integrals inside the integrand. And of course, it depends on details. And this solution is insensitive to the I epsilon prescription. Again, at 3 loops, and this is important to remember at least for the next 5 minutes, we find polylogarithms and up to weight 3. Now, this is, of course, not a full solution. We need also boundary conditions, which are obtained from regularity of the solution, that is absence of strange singularities, and also those that aren't fixed by absence of strange singularities are fixed by explicit calculation at y equals 1. Y equals 1 really means v equals 0, so it's just 2 particles sitting. And this is these boundary conditions are sensitive to the I epsilon prescription. Yeah, that's yeah. So basically, nominally each of these integrals one would need to evaluate it at one point. Now, this is all polylogarithmic. Well, the world is not polylogarithmic. It's not only polylogarithmic. If it were, then we might be out of business. Well, some of us might be out of business. I'm sure there would be other businesses to worry about. And there is a lot of work that has been done on non-polylogarithmic, on elliptic integrals. Some by people in this room. Where are you? And here at 3 loops, it happens that there is there is a polylogarithmic sector that is built on this particular integral, which is some complete elliptic, the square of some complete elliptic integrals. At 3 loops, again, it appears only in the potential region. And at the time we worried about this, there was no canonical form. This has been developed by work of Lapa, Hen, and Wagner, and also a different method for these particular integrals by Lapa, Kelin, Jingwen Liu, and Rafael Porto. The way we dealt with them was we had some idea what the function should be from attempting to solve the differential equations. And then we made an ansatz. And we computed some. We solved the differential equations to a sufficiently high order in y-1, 400 to be precise. We used about 60 orders to fix the coefficients, and then the rest to confirm. So when everything is said and done, this is what it all collapses to. These R's, I'm not going to show them to you. They are rational functions. They are not terribly disgusting, but they're not particularly pretty either. But the bottom line is that even so, this is a remarkably short and compact answer, given that it's the result of a 3-loop calculation in general relativity. There are a few things that are worth emphasizing. One is that it's a polynomial in the symmetric mass ratio with degree 1, which is the integer part of 3/2. So everything hangs together. There are these complete elliptic integrals that I mentioned. They always come with pi's for whatever reason. And then we have some logarithms and some Li2s. Seriously? And some Li2s. Now, as it turns out, if you look separately in the potential region and potential and radiation, this is not true. There are some more complicated polylogs that appear, which cancel when everything is put together. The other thing that's worth mentioning, which I asked you to remember, is that there were some weight 3 functions in the solution to the differential equation to the requisite order. All of those go away. So one question that is at this point the elephant in the room is, why do they go away? Can we see this without actually computing them? And can we use this to predict something, or at least make our lives easier at the next order? I don't know how to answer any of these questions, but maybe Andrew does. No, because those were ruled out already by the regularity of the solution. Yeah, the differential equation. So sorry, let me rephrase. Differential equation without fixed boundary conditions has all sorts of crap. Once the boundary conditions are fixed, then there's no more crap. Yet those functions still cancel. The weight 3 functions still cancel. And there are further weight 2 functions that cancel just with complex arguments. Yeah. Okay. Now, we don't know how to use this. It happens over and over again. We're going to see this. We may not see this. It happens over and over again. And of course, it would be great to understand how to use these, such features to simplify our lives. Now, back to physics after all of this, we get to compare with results obtained by other means being classical GR methods. They are available up to 6 post-Newtonian order, and everything agrees. There has been an all-order in velocity verification of these by Lapak, Helin, Zhengwen, Liu, and Porto, and also by Jakobsen and Jan Plether, Gustav Mogul, Benjamin Sauer, and Shu, and also by Damgaard, Hansen, Planté, and Van Hove. And for a while, there was an issue that these other methods, at least some of these other methods, were producing some order new square terms, which seemed to be breaking the good mass polynomiality property that we found and that was expected. And that issue was solved not too long ago, basically last week, and by Porto, Roiban, Yang. Okay, so everything hangs together. You seem very puzzled. Okay. Right, but ultimately the proof is in the pudding, as they say, or at least as they say in the UK. Right. So I was trying to motivate some of this enterprise as a quest for precision and getting higher orders in GR to match numerics. And it's worth trying to compare how that happens, how that fares. We didn't do that comparison. It was Damour and Retenio who did it. And they used potential conservative results, such as those that we obtained. And also they were supplemented with dissipative effects due to obtained by Dlapa, Kelly, Leonif, and Porto. And what you see here, excuse me, is a scattering angle which includes conservative and dissipative effects. The black dots are numerical relativity for scattering. And these lines, the curves, are various approximations and resummations based on these, based on the analytic results. And the ones that includes the three-loop results that I described and the corresponding radiation effect match to about 1% the results of numerical relativity. And there is, of course, clearly from the plot, a steady increase in the precision of that comparison. So this gives motivation to go further. All of this has been, there is further, I should perhaps emphasize, this particular plots refer to one point in parameter space. The comparison is not as brilliant at other points in parameter space, and this, in fact, indicates that we should go further. Yeah, anyway, we should go further. Yeah, I should perhaps add that since the Damour and Retenio paper, there has been more progress on updating these comparisons and making them a little bit better. And also, all right. So now this is three loops. Now, what about higher loops? Since we were motivated, well, the community was motivated. There, the story is more complicated and it's not finished. But the idea is to attack that problem in stages. First of all, it's useful to embrace this self-force organization, or the fact that there is this polynomial in the symmetric mass ratio. And because this polynomial is itself, the whole thing is gauge invariant. These m's are independent of nu, therefore they are separately gauge invariant. So they make sense to be computed independently. So it makes sense, again, to embrace this, compute each of these guys separately, and perhaps also learn from simple theories and import that knowledge that we gain to the more complicated case of general relativity. So we did, as a warm-up, we did QED at all three polynomials, one the probe, the 1SF, and the 2SF. 1SF, that is the order nu square. The conservative result in general relativity was recently derived in a very nice paper by Riese, Jacobsen, Mogul, Plewka, Sauer, and Uzovic. We did N equals 8 supergravity, 1SF, and 2SF is in progress. The 2SF conservative, it's complicated. It involves integrals that look like these, which are not terribly friendly. But they nevertheless seem doable. Including radiative effects is more complicated because, again, of the integrals. Radiation comes with an extra factor of the momentum, so to speak. One is interested, for example, in the momentum or the energy that's being lost in outgoing gravitons. Therefore, one needs to compute something like an expectation of a momentum operator, which adds some more tensor structure to the various integrals I was describing. At 4 loops, the integrals have 22 indices, meaning that there are 13 propagators and 9 irreducible numerator factors. 9 possible irreducible numerator factors, and there are 8 or 9 of these. So there are a lot of them. And also there are up to 4 doubled propagators. These doubled propagators come from the expansion of the matter propagators in so we have this 1 over p dot l plus l square p dot l. So these are the doubled propagators. So because of this expansion and because of the classical limit constraint, we have up to 4 of these guys. So, well, not terribly friendly. The IBP, given the complexity, the IBP reduction requires a fair amount of care, which at 1SF we managed to do by tuning FIRE and also using private codes. Dries et al. Tuned properly Kira to achieve to manage to do the corresponding GR calculations. And there are also things that need to be done to the integrand to actually, or at least to the input of the various IVP reduction codes to make them complete in finite time. In particular, identify integrals across various families, by which I mean that as one IBP reduces integrals in some family, one collapses propagators, then integrals start looking the same. And it's useful to do that reduction for those only once rather than every time in every family. It's also useful to restrict to a particular dependence on Q, namely the even powers of Q. The odd powers of Q are, of course, interesting if one cares to have an independent check, an internal consistency check of the calculation, but to actually get the classical answer, it's only the even and, in fact, highest power of Q that's important. And as it turns out, it's also in the classical limits, there is also something very interesting that happens, namely that as one takes cuts of various integrals, it's possible to planarize certain non-planar integrals. And that is also something that is extremely useful. All right, so what kinds of integrals do we get? Well, in QED, there is a canonical form for these integrals. And the kernels, or the letters, they are given by these. They are the so-called cyclotomic polynomials. There are no elliptic integrals in QED. And the final answer has, again, this good mass polynomiality form. There are 12 non-trivial functions that appear. And there literally are functions up to weight 3, as one might expect. But they are all, even though these are more complicated functions than Li2s and 3s, the result is only in terms of Li2s and 3s with real arguments. Now, more structure that we don't understand, the coefficients here, R1 and R2, have poles in strange places. So the physical region for sigma is 1 and above. 1 corresponds to 0 velocity, and above corresponds to non-zero velocity. So at 3 loops, we had a pole in the rational coefficients that appear at sigma equals 0. We didn't know how to use it. We still don't know how to use it, but it's there. At 4 loops, there is this 0 continues to appear in the coefficients of the 1SF terms, which were the only ones that existed at 3 loops. But in the coefficients of the 2SF integrals, there are further poles at sigma plus or minus a half. Again, they are unphysical, so they're not terribly bothersome, but one cannot stop wondering whether they nevertheless have a physical meaning. And if they don't, maybe they can be used as a means to bootstrap, or at least as a means to constrain something. They are there, they must have a use. The other observation is that even though there are here 1, 3, 4, 5, 6 letters, the amplitude is simpler. It really depends only on 4 variables. So one might wonder, why does that happen? I can't answer that, but one can nevertheless answer, why does that happen? And is it possible to bypass some of this enterprise and go straight for the amplitude and avoid computing separately the master integrals, especially those that are complicated and they somehow cancel or combine? I don't know how to answer that, but maybe this is motivation enough for some of you to think about. All right. Now, there's more structure, again, the kind that we don't understand, as we proceed to gravity. There is an elliptic sector which builds on the elliptic sector that sort of builds on the elliptic sector that appears at 3 loops. In fact, this integral obeys the same Picard-Fuchs equation as the corresponding 3-loop integral. There is the alphabet in n equals, so the set of variables that can appear in the 1SF amplitude in n equals 8 is listed here. So the size is this guy. So these are the elliptic letters, and everything built on them will be elliptic integrals, and more complicated things involving integrals of elliptic integrals, which in fact don't appear. Now, the interesting part is that, which happens both in n equals 8 supergravity and also in general relativity, is that all of these guys go away. They're not there. I mean, they're there integral by integral. I put things together, they all go away. So, of course, the obvious question is it possible to use this, first of all, to predict that this happens? And once it's predicted, can we use this without walking the IBP path? And this way simplify life. This is particularly interesting as important. If we learn how to do this, it would be extremely useful as we go to 2SF, where we know that there are more complicated integrals, which relate to Calabi-Yau manifolds. In particular, this one, which is a solution to this fourth order Picard-Fuchs operator. The question remains: does it's certainly there in the solutions to the differential equations, even after boundary conditions are imposed. So the question remains: does this actually survive in the amplitude, in the 2SF part of the amplitude and observable, or does it cancel? And if it does cancel, is it possible to avoid seeing it altogether? Nevertheless, even if it does cancel, it's important to evaluate it, because sooner rather than later, sooner meaning at the next loop order, there will be friends of his that will come. And without understanding the analytic properties of this one, then their friends will be a lot harder to deal with. So, and if you want to go further, the information is relatively scarce, but as one goes beyond 4 loops, one can, it would of course be great if we could figure out, if somebody could figure out the space of transcendental functions that could appear there. Even if it's overcomplete, it will be a first step. Or evaluate some of the integrals that we will undoubtedly encounter at that order. Here is a tiny list. There are way more than these. And also these are sort of schematic because by themselves, they are not classical. One has to dress them with sufficiently many ISPs to make them classical, but they're there. Here are some examples that are worth looking into, especially these, especially the last 3, but of course all of them. All right, so I have 15 minutes left and another 30 slides. The 30 slides is not a joke. But anyway, the idea was